Okay, thank you. Hi. Yeah, well, some guys are still coming in. Just for the record, that t-shirt is not the same one I have right now. I filmed that video like a month ago. It's a different one. We have lots of them. So, yeah, guys, just take a seat. But I will slowly start. Yeah, after this embarrassing video of myself. It's very strange watch myself. And I now understand what the keynote speaker was talking about. I cannot see a thing, so if you have a question, just shout at me, okay? And I will try to answer them somehow, blindfolded. All right, so the talk is named Performance Testing Done Right, and I would like to talk about some maybe small things, caveats, which can go wrong during the performance testing. And I come from the company called Hazelcast. Actually, this is my first non-Java related conference. So how many people are familiar or have heard of Hazelcast? Can you show hands? Okay, that was expected. Not so much. All right. Sorry. No, nothing. Okay. So, okay, I was expecting that. So what we do, why I'm mentioning this? What we do in Hazelcast, we do three products. One of these, the best known for us, is Hazelcast IMDG, in-memory data grid. Long story short, distributed cache, so it needs to be very, very fast. Hazelcast Jet, which is a streaming processing engine, also has to be very fast. And we have now Hazelcast Cloud, which is a managed service of these services, so we can try out, without any installation, just like Elastic Cache or, stuff like that. And why I'm mentioning this is, for us, performance is everything. If we're not fast, we're useless. Who would use a slow cache? Who would use a slow processing engine, especially if it should be low latency? So we pay a lot of attention to performance and performance testing. Before we start, I would just like to do some quick terminology recap. Just we're on the same page, and there are no misunderstandings in these completely basic things. So what do we actually measure when measuring performance? There are two basic metrics: throughput and latency. Throughput, okay, this is they are both very easy, but throughput is the number of operations that you do per some time unit. So you try to do as many operations as possible, in a second, in a minute, whatnot. And latency, or so-called response time, is measuring the time from the start of the operation, sending a REST call, calling a method, I don't know, you name it, to receiving the answer. So stopwatch thingy. Send it, stopwatch back, and count the time. So these are the two basic things that we measure. Of course, there are other performance measurements like memory consumption and I don't know, stuff like that. Also, sometimes even energy consumption is named as a measure of performance. But we'll be talking only about these two in this presentation. Also, we distinguish between several types, and I would like to do a category of two types of performance tests. One of them would be the real performance test, the throughput and latency test, where we actually get the numbers as an answer. We get this many operations per second. Our latency is this much, and we get the numbers from those performance tests. The other category would be stability, which is where you have your system, you try to do extreme load on it, as many requests from as many clients, maybe some crazy conditions, doing network partitioning and crazy stuff, and actually you want to know if your system can survive that load. And the answer is yes or no. This is the big difference, actually. So, and I will try to defend this categorization later on. The throughput test is, as the description says, doing as many operations as possible, right? So you can make it as a little while loop, and sending the calls, sending the operations. But the latency test, in order to be more precise, you want to fix the throughput. You want to measure the latency or see the latency behavior at the fixed number of operations, so it would be comparable. Because this is one of the key things, the number one thing that I see see being mistaken very often. So let's talk about that in next minutes. My presentation is divided into 5 so-called problems, 5 things that I would like to mention that I see reoccurring over and over and explaining over and over to other engineers, customers, and yeah, you see a lot of these things happening all the time. And for me, these are the things that I wish somebody would have told me 6 years ago when I started being interested in performance testing. And you know, now it seems obvious to me, but apparently sometimes I come to conversations where it might not be so obvious. So I will always describe the problem, or try to describe the problem, show them hopefully a real world example, and then propose a solution or some takeaway, let's say. So let's start with the number 1, which is, I already started it, is not distinguishing between the latency and throughput tests. For me, this is one of the basic ones, because you know, fundamentally there are different metrics. What people do very often, engineers, customers, you name it, is that they, you know, do a throughput test, so making as many operations as possible to the system, and then comparing the throughputs and latencies from that one single run. So in this scenario, let's say we have implementation 1, implementation 2, and we want to decide which one's faster, right, to go further in the development. And so let's measure the performance of this solution, and do it like this: throw the throughput test, and then look at the latencies as well. I see where this is coming from, because the metrics are related. This is what we subconsciously we know it's related. Like, if I can tap a beer in 30 seconds, I can, as a latency, I'm a Czech person, obviously, so beers, and so I can do 2 beers per minute. But if I make, you know, a beer in 10 seconds, I can do 6 beers in a minute. So we kind of intuitively think that these metrics are related, so we tend to look at them all together. But it's not always the case, and I'm going to show you the example. And also, we might not, if we want to do it precisely, we want to be like as precise as possible. You know, when you're doing a throughput test, at one run you will get like 1,000 operations per second. Then you will get 1,002 operations per second, you know, in the second run, because it will always fluctuate. It's never the same. It's not deterministic completely. So how can you compare latencies from those 2 runs when the throughputs were actually different? So there will be some jitter. Let me go to the examples where even fundamentally the metrics are not related to each other. So imagine the first scenario. This is a scenario where the latency is improving, but the throughput will actually might be worse or the same. So in the I'm for the first time using the laser operator. Okay, so on the left side you see like a sequential. You know, you're sending the operations and you process them as they come, right? So the query 1, query 2, no matter how long they take. In the second run, that might be, and this is actually like a real case, I'm not making this up. So in the right side, this is like a fair round-robin scheduling, time-boxed scheduling mechanism. So you start executing the operation, and once some time frame elapses, if the operation is finished, okay, good. If it's not finished, you pause it, and then you resume it in a round-robin fashion. So if you look at that, what does actually happen is that, okay, for the query 1, for the operation 1, we get the answer later, okay, some later. For the query 2, we also a bit later. For the query 2, we also get the answer a bit later. But for the queries 3 and 4, we get the answer much sooner. This is like an example. So you are actually improving by far the latencies of query 4, query 3. We're making latencies of query 2, query 1 a bit worse. But this is an illustration. This is what happens. So in this case, what actually happens is that the latency is improved, the throughput is not improved. It's the same, and actually it will be probably worse, because like pausing and resuming the operations, it will take some overhead, so it will actually worse your throughput, you know. And if that's something what you want, it's okay. But if you measure, so we see that the latency and throughput can be completely independent. So if they are independent in this case, well, let's test them independently. Okay, let's see the opposite direction. So the throughput would be improved, but the latency will be maybe worse or the same. So this is just a simple example of web server adding more parallel threads to a web server. Okay, so if one thread is processing the requests, I will still process it at some time. If I take 10 response threads, I will process 10 in parallel, so improving throughput theoretically by 10 times, but the latency will not be improved, or it will actually again be worse probably, because you're putting more load on the system, so it will not have the resources, you know. So it will actually go the other way around. It will not be intuitive that the lower the throughput, the bigger the lower the latency, the bigger the throughput. The intuition doesn't hold anymore. Obviously, this is the case of multi-threaded, parallel executions. So it's something to keep in mind, that it doesn't have to be always the way. And the takeaway from me would be to always distinguish between the latency and throughput test. If you want to do a latency test, you're interested in latency, you want to fix the throughput to eliminate yet another moving variable, which is the throughput. Also, when sometimes doing benchmarks for the customer, it takes a lot of time to actually realize what test they are interested in, what is the use case. I mean, they will always say, okay, let's do the throughput test. You know, comparing, let's say, the technologies, you're doing a benchmark against your competitor, and they will always, like 95% times, they will tell you to, okay, let's do a throughput test. Let's send as many operations as they possibly can, and then see who gets the higher number wins. But in production, they know that they will have, let's say, on average, 200,000 operations per second. They will never go above. So it doesn't make any sense to actually push the technologies to the limit, because you don't know how they will behave. You're interested in the comparison at that production scenario. So we spend a lot of time sometimes explaining to customers that, okay, this is actually not what you want. Even if you want to take a right choice, and not just because we are better in that scenario or something. No, I'm not trying to win the customer by lies, but you want to test in the real case scenario. So that's the first takeaway from the reoccurring problem number 1. Let's talk about another one. It's very sometimes when I ask like how many stressors, how many threads, how do you calculate what load do you use for your performance test, and how do you determine it? The answer is usually like, I don't know. I tried it. So the problems here can be that if the load is not, let's say, ideal or reasonable, it may distort your performance numbers, and thus making you do the wrong decision. Implementation 1 or implementation 2, you choose the wrong one. Because stressing the system over the limit is basically a stability test, and I'm getting back to the slide number 2 or something, that for stability test we take the yes/no answer, but for what we want to do a performance test, we want to actually look at the results. So the question is actually, how do we know that we're not stressing the system over the limit, right? And also it can go the other way around. If you're not put enough load on your system, it may be hiding the real performance. You're not actually testing what you want to do. I'm gonna show you the examples of this. Oh, okay, down. So yeah, I hope this line is kind of visible. Okay, so let me explain what this chart is about. So the red line is 8 clients, 8 stressors, 8 something, you know, 8 machines or 8 processes doing load on your system, but they are on one physical machine, because, you know, usually you don't have the luxury of having all the stressors on a separate machine, because of, you know, your performance lab is not that big. You don't have it costs a lot of money. So what you do, for instance, is to put number of stressors on one machine, and you have multiple machines. Okay, so this is the red line. Okay, this is the result for it. Then I'll add 16 clients to that same machine. That's the blue line. It's right here. So we see, okay, Hazelcast is really cool. It scales, you know, it basically doubled the performance. So yeah, very cool. Let's continue further. The green line is adding 8 more clients to that same machine, and I see that the performance is completely stable. Completely the same, sorry. It's completely the same. So the first interpretation might be, okay, we just hit the limit of our system. Our system cannot do any more operations per second. That's a valid point. Let's test it out. But the pink line here is having 24 clients, so the same amount of clients on 2 physical machines. And you see the big gap in the throughput here. So what is happening? You know, intuitively there are 24 clients, so it should, 24 stressors. The result should be the same, basically, and it's not the case. The reason what is happening here, this is again real example from performance testing of a Hazelcast with the clients. What is happening here is that the 24 kinds of stresses is just too big number of stresses on that particular machine, causing that the stressor machines, actually not the server ones that we are actually, not the system that we are actually testing, but the stressors are fighting over resources, CPU time, memory, mainly CPU time, and they are not able to produce as many operations on the system. Okay, but let's I just told you, like, why would you believe me? Let's prove this theory. This is a chart from the same run of a system context switches. So you see that number of context switches for 24 clients on one machine is much higher than 24 clients on 2 machines, obviously, because it's on 2 machines, so it's 12 and 12. But we see that the overhead of context switches is actually causing fight over resources in that particular system. I have like 10 more charts to back it up, but I don't have the time to show it all, and it's boring. So, in other words, we know this because we tested it. There is no other way of knowing this because every system is completely different. Let's go the other way around, when the load is not sufficient enough, when it's actually hiding stuff. So another chart, we're doing again, stressing the system. With the red line is one client. We have a multi-threaded client in Hazelcast. So it's one client, one Java class, let's say, and then you do 4 threads using that particular client. So this is the throughput for one client per 4 threads. And the blue line is 4 threads per one client. So one client per 4. So these are 4 clients driven by one thread, and this is one client driven by 4 threads. In the end, it's 4 threads. It's 4 threads driving the load, making the load. So again, the intuition says the result should be completely the same. Apparently, it's not. What's happening there? In this particular case, it's happening that our multi-threaded client is super multi-threaded. Is super optimized for a multi-threaded use case, because that's the real use case. We don't use our client from a single thread usually. So it's designed in a way that you have like a thread pool of IO threads, then a partition threads or executor threads. So there are lots of different thread pools, and they are like sending the messages over the other. That's a design choice, completely valid. But what's happening here is because it's only one thread per the client. So what the thread pools are doing is that the thread just does some small work, send the work to the next client, and goes to sleep. This one wakes up, do the work, goes to sleep. This one, etc. So there is a lot of sleeping, pausing the thread involved, which is causing a massive degradation in performance. In the second case, is that the single client, all of his thread pools are more busy, so there is less sleeping, so there's more performance. They are doing more useful work. And again, the only way that I know this is that I tested it. We tested it. We are aware of this architecture design, and so what this means actually is also we cannot recommend using the client from just one single thread, because the performance would be suboptimal. But that's not the point here. The point here is that I want to compare my implementations, if this optimization is super cool, but if I put too small load on the system, the other problems like context switching or sleeping, of the threads and waking up, doing the not useful OS work will hide everything in the system. Actually, then we tested with the optimization. If we do a proper load, it's actually much faster. But that's the case. So what you want to do is get to know the behavior of your system. By this I mean that you should always start slow, do step by step, like this origami, 3 simple steps completely. So you start slow, you do 8 threads as a stressor, or 8 stressors, then you do 16, then you do 24, then you spread it there on several machines, etc., and observe the behavior. Watch behavior of your system. Otherwise, you cannot know which is the optimal or suboptimal load on that particular case. I hope that does make sense. But the only way how to do it is there's no golden rule. Okay, let's use 1/3 of a CPU something, I don't know, threads. But it's system specific, and also our competitors, it has different different rules. Let's say different optimal stressing level. Let's go to problem number 3, which is just throwing away information. For me, it's something that I don't really understand, but it's happening very, very common. That we measure, we do super cool. Okay, let's say that we distinguish between the latency and throughput test. We go for the latency test. We have the optimal number of stressors. Our system is performing very well. And then we do all this testing. It takes a lot of time. And then we compare only averages. Doesn't make any sense. That's the problem, because it's hiding information. Sometimes the people are showing just an average. In better case, but still pretty bad, they're showing also minimum latency and maximum latency. In better case, they're showing also some selected percentiles, like 50, 75, 90, 91, 99.999, etc. Even better, you can show the whole latency distributions to get the full picture. But it's still not everything you can do. You can watch for much more. Just to illustrate that problem, let's say that this is these are 2 measurements. This is the implementation A, implementation B. We measured some. This is kind of artificial example, I admit it, but it happens. It's just much harder to get a understandable example of it. So you see, when you compute all the averages, minimum, percentiles, and stuff. So okay, so the average B is better than A. The lower is better. It's latency, response time. Okay, in minimum, A is better than B. Maximum, B is better, and then A is better, and then B is better. So how do you decide based on these, just these metrics? How do you decide which implementation is better in latency? I don't know. I seriously don't know how I could decide based on just these metrics, because I don't have the full picture. And this is what I understand, that it's very nice for publishing blog posts that, okay, average latency is this, and average latency of the other one is that, but it's not showing the full picture, because you know you're skilled mathematic guys. You know you know that average is just hiding information. Any good statistic person would tell you. So this is what you can do more, is that showing the whole latency distribution. This is a chart generated by a very good library named HDR histogram, made by Giltene. And you can see from here, so on the X, these are the percentiles. Okay, so the 90, because we're at Hazelcast, we're interested in the 90 plus. We know how it behaves here. So this is an example where, okay, the 90 percentile is something, but for the red line is much worse, you know. And so here we see that all the percentiles of the blue line are actually better than the red line. By the way, this is the exact chart that is, if you remember from problem number 1, doing the round robin time boxed scheduled, you know, fair execution. This is exactly the optimization in the Hazelcast. This is there was no improvement in throughput, but this is the improvement on latency. Sounds pretty interesting, I think. So it's a good idea to print, you know, this is just a histogram. So print all the information. Histograms don't hide information. But I said, okay, that's still not good enough. What can you do more? What we do, for instance, is that we calculate also like a interval latency ones. And what this chart shows is actually is from the same run, by the way. It's from the same run, the red line. So in here you see that the latency distribution is pretty bad, or you know, there's some progress, but you don't see if maybe there are some other problems in performance. And this is the latency interval percentile chart, which means that we on every second we calculate the 50 percentile, or 70, 75. We calculate the percentiles for that particular second. So in 10 second, the percentile 50 was this. It was higher. In 40 seconds, it was higher. In minute 30, it was way higher. So from this, because this is the latency distribution chart, the previous one will not show you the progress over the test time, over the test running. But the interval latency percentile chart will show you that the latency is actually increasing over time. So the performance is decreasing. There's something wrong, you know. What happened in this particular case? Yeah, it was, I'm a Java person, so the first chart to look at was GC heap sizes, and this is where it was a memory leak. You see here I have a heap young size maximum, so it's increasing. It's actually doing a memory leak, and that's another important part, to generate as many charts as possible. Watch every single possible aspect of the system: memory, CPU time, network, throughput, latency. I don't know what's left, context switches, I/O stuff, and then look at those charts as you're doing step by step, as in the origami case. You actually want to see the effects on every chart. If you have a theory, confirm it with the other chart. So my takeaway from that is, in general, that this is not just for the latency testing. I made it general a bit. Generate as many charts as possible. Watch for as many aspects of the system that you possibly can. And when you're doing the performance testing and you see something is happening, I would expect, for instance, when I add more stressors, I would expect that the garbage collection will be more often, because there are a lot of more entries to be collected, etc. So it has to make sense. You're making a puzzle, basically. You're adding pieces to the puzzle. This is just the link to that HDR histogram library, which calculates the percentiles and distributions, etc. for you. Very useful for latency testing. Now the problem number 4 is somehow actually very trivial, but it can mislead you a bit. So say you have, when you're doing performance testing of your system, say you have 2 types of operation. Typically read and write. That's for our case the most basic operations. Read from the cache, write to the cache. And you want to test again some real life scenario. For the caching environment is usually like there are 80% of reads and 20% of writes. That's like a typical typical scenario, very frequent. And what might happen is there a baby on the call, on the talk? Oh, okay. What might happen is that you accidentally end up with a different ratio that you actually wanted very easily, and let me explain why or how. So let's say I get this scenario from a customer. Okay, 80-20 ratio. Okay, good. So what I do, my first intuition can be that I start 80 stressors that will do reads and 20 stressors that will do writes. 80-20 ratio it is, right? But you have to realize that the operations might not take the same time, right? Writes are in general slower than reads. So let's, for example, see that the latency of a read is 1 millisecond. The latency of a write is 2 milliseconds. This completely possible, completely valid. So let's see, just a small mathematics. So read client will do 1,000 operations per second. Write client will do 500 operations per second. Still pretty valid. Okay. So now I will let the performance test to run for 60 seconds. Okay. This is for 5 minutes. So I'm doing 1,000 reads per second. I'm doing it for 5 minutes. I'm doing it with 80 clients. The same for writes. You see the numbers. It's a simple math. But the resulting ratio is 88-11, which is not 80-20. Right? Because you forgot this very important, premise that the operations are not equal. They are not taking the same time. This could be perfectly valid scenario. It actually sometimes, or quite often actually, but it's sometimes it's completely valid scenario that you have just read clients and just write clients. But you have to know if this is the case, because let's say in 30% of the times in my experience this is the case. In 70% of the time it's not the case, that the client is actually sometimes doing read, sometimes doing write, that based on probability. So the solution to it, so first thing is to get to know which case it is, right? Really make sure before starting the scenario that okay, this is the case, I want it this way, etc. But when you want to solve this problem, you can do it based on probability. It's pretty easy. Generate random number and then show an falling into interval. It's solvable kind of. And the last thing is performance regression, which is for us very problematic. Because if we are not fast, we're losing. We cannot come back to our previous performance. So it's like dating ex-girlfriend. It's never a good idea, I think. So sorry if I offended anybody. I got recently married, so I have a lot of jokes like this. So let me show you how we do it in Hazelcast, because the solution to it is to actually do the performance test regularly on daily basis, store the results, analyze the results, possibly automatically. And there is again no golden rule, but the advice, the must-have is that you have to do the performance testing on a regular basis automatically, because nobody will ever find an hour of his time or her time to do the performance testing and then compare the results. So let me show you. This is the part that I fear the most, because this is actually a live demo, basically live system that we use in Hazelcast. So what this is showing is like one one scenario with get throughput of throughput test of 1 kilobyte value with map. That's not important. And we do this. Every point in this chart is a performance test, one day by day. Automatically automated in Jenkins, uploaded to this application named perfRipple. And so we see, when you look at the chart, you actually see that it fluctuates a bit. We're actually working on the problem as well, but it's a never-ending story with performance testing. It will always fluctuate. But for instance, in here, I can see clearly that we hit some performance ratio. Yeah, maybe this one was more obvious, but actually this one is a hardware fault that occurred last week, and we're fixing replacing a memory DIMM tomorrow. So yeah, that's a problem that we're solving right now. But in general, these charts are live, so they are regenerated every time some new result is uploaded to the system. And we can easily, what we do also, I hope the connection is good now. Okay, let's log in, re-log in. Okay, perfect. So what I actually can do, we actually tag the we store as much information as possible on that in the system. So if I see that there is some kind of problem, I also upload like a commit hash to that particular run, so I can see that, okay, this regression happened between this and that commit hash. So that's like our tool. This tool is open sourced, is named perfRipple. I was project lead of that in Red Hat for a few years, but now I don't have any more time in Hazelcast for it, so I handled the leadership back to my former colleagues in Red Hat, but it's still open sourced as far as I know. So we're hitting very close to the 2-minute time. Let's is it including the QA? No. Okay, perfect. So I have these are the useful resources. I very much recommend you to watch this if you're interested in latency measurement. This presentation from Gil Tene, very great guy. He's a CTO of Azul Systems, the JDK provider. This talk is just brilliant. And there is also a 2-hour version in Hebrew if you're interested. So this one like an hour. And I'm gonna use those 1.5 minutes to show you one quiz, one thing that might go wrong, that might not be obvious as well. And so we have a setup. We have 2 clients doing writes of values, 1 kilobyte, 10 kilobytes, 100 kilobytes to the system, and we get these throughputs. So 1 kilobyte, we have 100, 10 kilobytes, we have 10,000, and 100,000, 10,000, and 100 kilobyte, 1,000. Based on these numbers, on this table, is there anything fishy? Like anything looks weird to you? Because I look at those numbers and I see a problem. Sorry, can you speak up? Anybody? Sorry? Okay, perfect. Thank you. Please come to me. We'll have a beer. I invite you. Okay, so yes, perfect. What's the problem? What might be the problem? It's you always have to count with the fluctuation, so it will not be precisely like 10 times better, 10 times better, etc. Right? Okay, I see. All right. All right. Yeah, actually, yeah, it's a good way to start. I see the thank you sign. So so the thing here is very quickly is that it's decreasing too regularly. Let's say 1/10, you know, the multiplication is still approximately the same number. It's never the case. It's not never like this. And what was happening here? The network bandwidth was just 1 gigabit. So if you multiply it, it's always 1 gigabit. So the network was the cap. So you would never get a correct answer from these questions because the environment was flawed. And that we figure out by looking at the network chart, like hitting completely straight line. That was very weird. All right, that's enough. That's enough for the talk. Now is your time for questions.